Good morning. As far as the midterm quality reports are going, I'm going to put them all in a folder and I'm going to assign everybody the review assignments this week. And so then just be looking for that. It'll be a shared folder, so just go in there and download the PDFs of the two that you're assigned. Okay. And so that'll be that way that works. You'll have 2 weeks to do the assignment, and then you'll get your comments back. You know, I'll send those. Yes, they may. I'll give you instructions on how we want to handle the comments. You know, and so then you'll have, I guess, to the end of the semester to make those changes to your report. So you should still be collecting your data every day and updating your control chart. So the final quality report will have all the rest of the data. In addition to this data, you're just going to expand your midterm report with the data from here to the end of the semester. Take into account all of the comments that you get from your reviewers, produce a comment response table, and then turn in your final report at the end of the semester. So any questions on that? I know there were a couple of people that glitched on the upload, and that's fine. I'll get those put into the folder as you asked me, so it's not a problem on that. Okay. So today we're going to be talking about some fun stuff. Everybody, I mean, how many people got into chemistry because they like to see like things burn and explode? Just me? Okay, so I'm not alone on that. And so we're going to be talking about that today, but we're going to be talking about the chemical basis of it. So I'm going to give you the chemical background behind burning, explosions, and so on, and detonation. But then when we get into the second or the third part of the course, we're talking about physical evidence then. So then we'll be talking about the physical effects of those detonations or fires and so on. So today we're focused on the chemistry of it. So the middle part of the course is on the chemistry and chemical evidence. So we'll be talking about what makes something burn or explode. Okay. So combustion is the second most common forensic analysis behind drug and toxicology. And so this is, we're going to be talking about the combustion basics. We're going to be talking about fires all the way up through explosions. So we're going to talk about the transition from combustion to explosion, and then explosive detonation. Detonation is a very specific phenomenon. And then we're going to be getting into how to make that detonation go all the way up to the most powerful things that we have today. And that would be weapons that use the nuclear force, the strong nuclear force. And so let's just start at the basics, the fire triangle. So you need three things for fire to be sustained. So we have burning of fuel with oxygen is a spontaneous reaction. So it proceeds without any external input. That's how we define spontaneity. Once it gets started, it just proceeds. As long as you have fuel, as long as you have oxygen, and as long as you have enough heat to get it started. So the heat is the activation energy. Once we get over that activation energy, then it's exergonic, which means it's spontaneous, and exothermic means it releases heat. So because it's releasing heat, it continues the burning. So it gives itself its own activation energy. Now, the way we prevent things from burning, because we're surrounded by combustible material, we prevent that by preventing the mixing. And so, you know, these keys, especially iron and aluminum, that's incredibly exothermic. And so why is my key not burning in my pocket? There's oxygen everywhere, okay? But it's because it's not mixed. If you were to powder that aluminum and get it mixed in with oxygen, then you have what we call a thermobaric explosion. So it produces an enormous shock wave and pushes things over. So mixing is key. So that's the way we fight fires too, is we somehow get that oxygen. We either attack the heat, like with mist, water mist, or we put in CO2 and produces a chemical effect, but it also drives the oxygen away, so it prevents mixing. Foam will also absorb the heat because it's got water in it, but also it prevents the mixing of oxygen and fuel. So even though we drive around with tanks full of gasoline, which are flammable, and airplanes full of jet fuel, which are flammable, I think the airplane's the best example. Whenever there's an airplane accident and you've got thousands of gallons of fuel spread out onto the runway, they show up immediately with foam trucks and they cover that with foam. And so you've got a barrier between the oxygen in the atmosphere and the fuel. If you can steal the heat, so you take away the activation energy, and then you separate the fuel and the oxidant, then you're in a stable situation. I wouldn't necessarily call it safe yet to you mop up all the fuel, but it's at least stable and it's not burning. Okay, this is why I'm a proponent of using fuel like hydrocarbons for all of our transportation needs. I think electric cars are cool, but I think it's dangerous to put batteries in these vehicles, because to get a long drive time, you need to have smaller and smaller batteries. You need to have a higher energy density. So what we're creating with these long drive time batteries are bombs, essentially. They don't necessarily detonate, but when they start burning, you can't put them out. Why not? Because of mixing. The oxidant and the fuel are millimeters apart. And unless you can get the oxidant and the fuel away from each other, because inside the battery you have the oxidizing agent and the reducing agent. That's the oxidant and the fuel. They're so close together, there's no way to turn that off. Whereas in a fuel spill, you've got oxygen in the atmosphere and you've got fuel, which is a liquid. You can put a barrier over that and separate the two pretty easily. I'm not going to say fuel cars don't catch fire, they do. But you can put them out. You can spray foam on there and you can put them out. So I just think that's one warning or issue that we have to overcome if we're going to get long driving batteries, is the danger of putting the oxidizing agent and the reducing agent right next to each other. So maybe there's a new kind of battery where we would have those separate and we would run them, in some other way. So that would be a technology that you guys could make billions if you would invent. So go do it. Okay, and then we also have halogens that steal the heat by their evaporation, but also it's a chemical effect. Breaking the carbon-chlorine or carbon-fluorine bond, it absorbs a lot of heat. And so if we spray chlorinated and fluorinated solvents on a fire, then we can steal the heat. And that sounds extreme, but if what we're storing is water sensitive, like art, then we might put in gas vapors that spray chlorinated and fluorinated vapors on the fire and put it out that way. And that's what we have with high-end fire retardant systems. So halon gas, they'll spray into a museum if there's a fire in a museum, and that way they don't spray water all over the priceless art. And that's an example of carbon tetrachloride. I was at a pharmacy museum in Texas Tech when they were opening their pharmacy school, and they had like a 1800s apothecary place, and it was neat. It had all the glassware, and on the wall they had this glass grenade, is what it was called, a fire grenade, full of carbon tetrachloride. Okay, with a dye. The carbon tetrachloride is not typically red. They put a dye in there. But it said, in case of fire, throw it at base of fire. So you had this glass filled with carbon tetrachloride. You throw it at the base of the fire, and hopefully it goes out. Okay, it's also crazy because that's a carcinogen. So maybe making a bad situation worse. I don't know, but yeah. And so this is that combustion continuum. And so on the far left we have burning. Okay, and it's in terms of the physical effects, we would get into like arson, fire investigation. We would look at the chemical signatures of arson and so on. You've got fuel such as hydrocarbons. In burning, the oxidant is the air. That's the oxidizing agent. Okay. And here's the key. If the fire is unconfined, then you have low pressure. So that's why we don't have explosions, right? We just have fires if it's unconfined. But if you start to confine it, then you're heating a closed container, and that's when you can have a boiling liquid explosion. So if you're heating a closed container and the liquid's boiling in there, it's producing a lot of steam or pressure, then it can blow the container. We call that a thermal process, and its effects are generalized, meaning in all directions. There's no directionality to it. But let's look at this piece right here. This speed of burn. That's an important distinction to look at, because if the burning goes from subsonic to supersonic, and we compare that to the speed of the sound in the medium, so speed of sound in the liquid or speed of sound in the solid material like an explosive, if that goes supersonic, then we're making that transition over to detonation. So that's our one sort of key thing: confinement and the shock wave that's going through the material. So as something burns, it starts to generate an energy wave. And the fastest energy wave is light. Okay, so light can go through the material. Well, maybe not visible light, like this can and this koozie are opaque, so visible light doesn't go through, but infrared light does. Okay, X-rays do. UV light may, in some instances, go, penetrate differently than visible light. And so light would be the energetic shock wave. You could have an infrared shock wave. And then you have the speed of sound. That's the molecules banging into each other. Okay. And none of this is at equilibrium. Okay, so we have an event, an energy release. Light goes through the material. The thermal shock wave comes later. But when that shock wave passes the speed of sound, then we can have a detonation. Notice the fuel goes from air, because air is slow. You have to have diffusion of oxygen into the flame to keep it going. Here we start putting inorganic oxidants, or maybe even organic peroxides, or nitro groups, and so on. So now we're putting the oxidizing agent inside the material. And so that's what makes it go from just a fuel to a propellant, something that produces a lot of gas, to an explosive. The way I like to think of this supersonic shock wave, it's got to be a mixture of infrared energy, maybe near infrared energy, because that's the only thing that can go faster than the speed of sound in a material. Think about what we mean by the speed of sound. The sound goes through the material by collisions. So you have a sound wave coming through, it hits the next group of atoms, and then that moves and hits the next group of atoms, and then that moves. So that's the fastest that material can move. Mass can move through the material, but energy can move faster than that. So when we start to build up an appreciable heat wave that's transmitted in the infrared through the material, and that's enough to create hot spots, and those spread and generate more infrared light, that energetic wave can go through the material, and that's how we switch from a burning, a deflagration, to detonation. And that's what this DDT stands for, deflagration to detonation transition. So deflagration is vigorous burning. I'll just put a little thing here. And that's many times for deflagration, you have to have the fuel as a part of the mixture. Like you can't just be, oxygen coming in from the atmosphere. You're going to have some sort of fuel source that's well mixed into the material, or air pumped into the system somehow. But it's vigorous burning. And then detonation is not a burning, it's an explosion. It's nearly instantaneous. Okay. So the basics of burning. I mean, you've got the fuel here. This is the reducing agent. And then the oxygen's coming in. It's the oxidizing agent. And so we have redox reactions taking place. So burning is a redox reaction. Oxygen is taking electrons from the fuel. That's what oxidation is. Oxidation is loss. Reduction is gain. So the oxygen is reduced. It's gaining electrons. It's producing water and CO2. And then also it's decomposing. That heat is decomposing the fuel. So this is our fuel. It's a cellulosic stick, okay? And it's turning black here because oxygen reacts with the hydrogen first and steals it and makes water. And this blue flame is typically the emission of hydroxyl radical. So here oxygen atoms has stolen one hydrogen. So now it's an odd species. It's not hydroxide. That'd be OH minus. That'd be an extra electron in here. This is hydroxyl radical. And so some of that light, as it steals that hydrogen, it's giving off light, H nu. Okay, and that's in the blue region. So we see a lot of those UV and those blue photons coming out of this reaction of oxygen with the hydrogen to produce water. And then some of that carbon is left behind, and not all of it is making CO2. There's also just some carbon solid that's hot. So that hot carbon soot is where the yellow flame is coming from. Okay. I used to think it was sodium. I thought, man, this wood has a lot of sodium in it, which it could, because it's a plant, right? But it doesn't give you the line spectrum of sodium. So if you look at the flame with one of our little spectrometers, like our USB spectrometer, you don't see the sodium line as this bright yellow orange flame. You see a black body curve, and you could use that to get the temperature of that soot. Okay, so it's a continuum. So it's not an atomic emission, it's a continuum of hot soot. If you have a really complete combustion, you don't see the yellow flame. Like your stove, you're burning methane in the stove, very little soot, so you don't see the yellow flame. You just see the blue. Of course, this would be the ideal case, is burning straight to CO2 and water completely. And so we'll look at these enthalpies of combustion as the best possible case of complete combustion. And so here's our, this is from the thermodynamics class. When we talk about enthalpy of combustion, we do a lab called the QSAR, Qualitative Structure Activity Relationship. And typically those are they're typically used in pharmaceuticals and other places where you're trying to find the activity of a substance based on its structure. So you could do this in forensics too. Like if you had, methamphetamine, and you're going to try to make a different kind of substance, or let's take heroin and morphine. Like they took morphine and they acetylated it. They changed the structure. What kind of activity would that have in the body? And so if you have a survey of enough drugs, you could look at the structures and see what they do in the body, and then come up with a statistical relationship. What happens when I acetylate these drugs and these different things? Maybe you see a trend, and statistics will tell you that, this is what you should try next. And so a way to screen through thousands of compounds without wasting a lot of lab resources. Okay, so that's the concept. It's a statistical relationship from the structure to the property, or from the structure to the activity. Activity is typically used when we're talking about activity in the body. Property was used for something like this. So this really should be QSPR instead of QSAR, because we're talking about combustion as the property. Now I thought, what is the simplest structure of a molecule? Just the number and types of atoms. So the molecular formula, carbon, Ca, Hb, Nc, Od. You just have A, B, C, and D, the number and types of carbon, hydrogen, oxygen, and nitrogen atoms. And so I thought, what if we just did a statistical relationship of the enthalpy of combustion based on the number of carbon atoms it has, and the hydrogen, and the nitrogen, and the oxygen. And this is the regression I get. So I can predict the heat of combustion based on the molecular formula. I don't really even need to know anything about the structure. The molecular formula is kind of a structure. If I've got more carbon atoms than this other person, then I'm going to have a different structure. So there's some structural information in there. And we get 99.62 R squared. That's pretty good. What this allows us to do now is this is our equation for, let's see. This is our equation for enthalpy of combustion in kilojoules per mole. So let's do acetone. Okay. So you know the structure of acetone. We can add it up. It's C3H6. And we can skip nitrogen since there's no nitrogens, and then we have an O1. So C3H6O. So our delta H combustion is going to be 32.1 plus 426.9 times 3. That's the number of carbons. Plus 88.2 times 6. That's the number of hydrogens. And then look, minus 163.5 times the 1 for the oxygen. Isn't that interesting? If I add oxygen to the formula, it reduces the enthalpy of combustion. And why is that? Well, because I'm ruining the fuel. I'm already oxidizing it. So acetone is already partially oxidized, and so we lose some potential heat that would come out of it when we burn it because we've added oxygen to it already. So let's see. We can see who's faster on the calculator if you want to do this too. So 32.1, 6, 8, 9, enter 3 times, and plus, and then 88.2, enter 6 times plus, and then 163.5 minus. So I get 1,678.5 kilojoules per mole. So, and this is a pretty simple equation to use. Okay, and when you do this for all these compounds, you can get the enthalpy of combustion per mole. What if we wanted it per gram? Okay, then we would divide by the molar mass. Well, the molar mass is also a qualitative structure property relationship. This is just the molar mass, the molecular weight, MW. Okay. So that's delta H of combustion divided by the molar mass. And so here we see the specific heat. When you see that specific heat, it's per mass, per gram, or per kilogram, but this is per gram. And here we see essentially all of the hydrocarbons are around 40. So if you wanted to just estimate how many kilojoules per gram there are in cardboard, wood, straw, hay, paper, those are all cellulosic materials, but still, any of the, like a good number for that is 40 kilojoules per gram. Okay. Now, when you get to these smaller things, especially hydrogen, look at that one, that's crazy. This is what gets a lot of folks very excited about using hydrogen, like for transportation and so on, because it's incredibly light. And so we get 120, we got 3 times more kilojoules per gram of hydrogen. But hydrogen is incredibly difficult to compress. So in order to carry hydrogen in a vehicle, you're going to need a pretty big pressure tank. And then you're running around with 9,000 psi of hydrogen in your car. And I don't really like that idea either. Okay, so now what's going on with all of these down here? These down here are alcohols, ketones. These are all the ones that are already reacted with oxygen. These are called oxygenates. Okay, and so this shows you that it doesn't make any sense thermodynamically to put ethanol in our fuel tanks. It's already oxidized. The only reason we put ethanol in our fuel is a political reason. It's just about negotiating with the corn farmers to find another outlet for some of their product. And so they always get that into the bills, and we always see that ethanol is added to the gasoline. It actually, it decreases the amount of kilojoules that we get out per gram, okay? And it also is very compatible with water. So humidity will get into your gas tank, and then that can cause problems with your engine, with rust and corrosion. So if you have small engines in particular, it's always good to get ethanol-free gas. And I don't think we have a source of that in Huntsville. In LaGrange, they have it, and we can get it when we're in LaGrange. But for weed eaters, lawnmowers, chainsaws, things like that, you'd want to use ethanol-free gas if you want that motor to last longer. Okay. So here's some tools of the trade in terms of keeping track of the heat that goes in, that comes out of these combustion reactions. Okay, so the heat generated is given the variable Q. And so here's your heat of combustion. This is per mole. And so typically we can estimate or calculate the mass of the fuel. And so what we're doing is essentially we're converting this over to moles of fuel. So this is a conversion from mass to moles. If we have the specific heat, then it's per gram already, and so we can just use the mass and multiply by the specific heat. Okay, so that's how much heat is given off by the system. we can use, in terms of calculating the force, we can use the ideal gas law. And so we can calculate the maximum moles of gas. And so we could look at our reaction and how much gas it produces, how much water in the form of steam, and how much CO2 it produces. And we can use the gas constant and the temperature of those products, the sort of mass estimated temperature of those products, to calculate the force in the room. Now, why would that be important? Well, that's important for your structure. You're going to generate a force in this room by a certain amount of gas being produced. It could push out the windows. It could destroy the structure. Okay. And then this is the important piece, this stoichiometric ratio. So firefighters and folks dealing with fire, they want to deal in mass. And so they're talking about the mass of the fuel versus the mass of the oxidant. So this is a mass ratio. So both of these are mass ratios. And we have the stoichiometric equivalence. So this is from the chemical reaction. So that the stoichiometric equivalence is from that balanced chemical equation, and then the system is the actual. So we calculate this phi, the stoichiometric ratio, letter phi, to see if we're at the stoichiometric ratio or not. So if phi is equal to 1, then we're in a very dangerous situation, because we have exactly the right amount of fuel and oxygen mixed together. So we'll see what that does in a second. So let's calculate the stoichiometric ratio for methane and air. So here's our balanced chemical equation. So our mole ratio is 1 mole of methane for every 2 moles of oxygen. What we want to do is we want to convert both of those to masses. Well, that's pretty easy for methane, right? Carbon's 12, and I got 4 more, so that's 16 grams per mole. But what about oxygen? We don't have pure oxygen in the room. And so we need to talk about the mass of the air that would give us 2 moles of oxygen. Okay, so this is our question. What's the stoichiometric ratio in terms of air, not of oxygen? So how many moles of air will provide 2 moles of oxygen? So here's our mole percents in our atmospheric composition. These are the top 4 species in air. We really don't have to worry about the CO2. The argon is about 1%, but you can just say, as a good rule of thumb, oxygen is 21% of the atmosphere. That'll get you there, okay, 0.209. And so 2 moles of oxygen, if we want to convert that over, there's 0.209 moles of oxygen and 1 mole of air. And so this is how many moles of air we need. Now we can convert that over to mass. So what is the mass of this air? So 1 mole of air has got a mass, it's this mole ratio here, all times the masses. So this is 78% nitrogen, and we've got the molecular weight of nitrogen. So we just have the molecular weights of all 3 of these gases times their mole percent. And so this is 28.9 grams of air for every mole of air. So that's a conversion factor. 28.9 grams of air per mole of air. And that'll be on your equation sheet. So you don't have to redo this whole thing. But that's a good number to know. If you want a mole of air, you need 28.9 grams of it. So if I need 9.58 moles of air, I multiply by that conversion factor, and I get 277 grams of air, which would contain the 2 moles of oxygen that I need for the stoichiometric amount to burn methane. And so here's our stoichiometric amount, 16 grams of methane, which is 1 mole, divided by 277 grams of air. And so we get this 5.8% by mass of methane in air. So that's the perfect stoichiometric amount of methane in air. So if we have that situation, like if we have a gas leak and it achieves something close to 5.8% in the house, the smallest spark just can destroy everything. So let's calculate that. So here's our example. Would a 5 liter per minute gas leak reach an explosive concentration overnight in 8 hours? So we have 8 hours. We got to make some assumptions here. Okay. At 60 minutes per hour, that's not an assumption, that's exact. Okay. 5 liters per minute is our leak. Okay. And so this will give us 24.4 liters per mole of methane. That's the volume of 1 mole of methane at room temperature. And then we've got the molar mass of methane, and we convert it to kilograms because we're dealing with a pretty large amount of methane. So we have 1.5 kilograms of methane in 8 hours. Now, how did I know how to do this? Well, I knew that I needed 1 unit at the end, kilograms, and I knew that I'm starting with 1 unit here, 8 hours. This is what I call a double unit. Everybody understand my terminology? It's a liter per minute, okay? So that's going to be used in the middle of the problem as a conversion factor, okay? So I start with 8 hours, and this is liters per minute right here. So I know I'm going to have to get out of hours and into minutes. So that's what I did first. Then I use this as a conversion factor. Now I've got liters of methane, and I want to get mass of methane. And so from this point on, you should be very comfortable with the problem, because you go from this right here using the ideal gas law, V equals nRT over P. So we got 1 atmosphere of pressure, room temperature, 1 mole, okay? So that gives us the volume. And then molar mass of methane, convert to kilograms, just to keep the numbers nice and small. So that's the mass of methane. Now, what about the mass of air in the house? We got to make some assumptions here. Okay. I guess you guys haven't been on the real estate market very much, but you know, a typical home, and it depends on the neighborhood, of course, but you know, 2,000 square foot is a decent assumption. Okay. And so 8-foot ceilings, it's not an extravagant home. So that's our volume in feet cubed. Okay, so then we have to look this up. Again, this will be on any kind of conversion that you might need on the test, will be on the equation sheet. So that gets us to liters. Then we go to moles, 24.4 liters per mole of air. Then we have that conversion factor that we just derived on the other page, 28.9 grams of air per mole, kilograms. And now we have 536 kilograms of air. So this is the ratio labeled SYS, not STE. STE is the stoichiometric equivalent. That's the perfect situation. This is the actual. This is what we have. Okay. So we're at 0.003%. Okay. I mean, yeah, 0.003. Yeah. And so we can take that and divide it by the stoichiometric ratio, and we end up at 0.05 of the equivalent amount. If it was a ratio of 1, we'd be at an explosive atmosphere. We're pretty far from that. We're 0.05 of that. So let's look at this. It's too lean. We call that when you have not enough fuel, way too much oxygen, it's called lean. If you have more fuel than you need, then it's called rich. So let's look at this. When that ratio phi is 1, so we're right here. When this ratio of phi is 1, that's the perfect situation, and that's an explosive hazard. So this explosion limit right here, that's the worst case right there, of phi of 1. when you're too rich, you're above the upper explosion limit. You see that up here, lower and upper explosion limit. So the UEL is the upper explosion limit. When you're too lean, you're below the lower explosion limit. So between these two spots is danger. Okay, and you can find these a lot of times on the safety data sheets. So you might have a solvent that you buy, you get a safety data sheet, you're looking through it for the hazards. Most of the time you look for things like it's going to be irritating to your eyes, it's going to be irritating to your skin, it's toxic, it's flammable, and so on. But when you look at the physical properties, it'll have specific density, it'll have maybe it'll have some vapor pressure information, but you'll see LEL and UEL sometimes. And it's telling you what the lower and upper explosion limit is for that gas. And if it's producing a lot of vapor, you need to pay attention. So now, we assumed one thing in our problem that may not actually apply. It looked like we were safe because we had a 0.05, but methane is lighter than air. And so that whole gas leak may not mix perfectly with all the air. Now, if our ceiling fans are running, it's a trade-off. It's running, that's good. It's diluting the gas with the air, but it's also sparking a little bit if it's a brushed motor. But since methane is lighter than air, it's going to collect up here around the ceiling, and so it's going to be in a smaller volume up there if the ceiling fans are off, and you're going to have a rich mixture up above. Then you're going to have the perfect explosive mixture, and then down here it's going to be too lean. So there may be a part right here where it's really flammable, right there in the middle. If you have a solvent and it's heavier than air, then you might have a rich region that's along the floor, a flammable region, and then a lean region. So you may be standing here, you're working in the garage, you're working on, maybe you're refinishing something, you're stripping the paint, and all of that solvent vapor is collecting around the floor, and you don't really smell it because it's a heavy vapor. But you could have a flammable situation, and if you have a source, maybe you come over here and you unplug something from the wall, and it creates a spark. Boom, not good. So you just got to make sure that you pay attention. Anytime you're dealing with flammable liquids, what do they say on the can? Use in a well-ventilated area. You don't want this to collect and create an explosive vapor. Okay. Now this is for traditional fuels. Things like our natural gas, right? Which is lighter than air, it's going to stratify in the top part. Gasoline, solvents, and so on, those are heavier than air. They're going to collect along the floor, okay? But still, where's the oxidant? The oxidant is the atmosphere. Okay. Now, when we get to propellants and explosives, totally different ballgame, because we're not using the oxygen in the air to burn the fuel. The oxygen is contained in the fuel, and that's what makes it a propellant or an explosive. So now we can look at the material itself. Let's say we have an explosive like nitroglycerin or TNT. We look at the material itself and we say, does that material contain enough oxygen to produce water, to produce CO2 within itself? So notice in this reaction, we have some explosive substance over there, Ca, Hb, etc. And in itself, it's producing CO2, water, nitrogen gas, and oxygen. Okay. So if it overcomes its activation energy, it can react with itself and produce all those gases, which push things over. Okay. All right, so let's look at this. This is how we determine how energetic the material is going to be. We look at this oxygen balance. And so you've got, this, you can check this, check my work. If you've got A moles of carbon, that's produce A moles of CO2. And if you have B moles of hydrogen, they come in pairs, and so it's B over 2 moles of water. If you have C moles of nitrogen, you're going to have, again, they come in pairs, C over 2 moles of nitrogen. And then oxygen is going to be the amount of oxygen minus the amount that's used for the carbon. So twice that of the carbon, because there's two oxygens there, half of that for the water, and there's no oxygen needed for the nitrogen. Okay. And because these come in pairs, we divide by 2. So you can check my work on that. That's the ideal reaction for carbon, hydrogen, and nitrogen. So let's look at nitroglycerin. Do we have enough oxygen in the molecule of nitroglycerin to completely produce as many gaseous products as possible? So this is the calculation that we're talking about. So we go through here. This is our formula for the amount of oxygen. If this calculation comes out positive, then we've got more oxygen than we need. If it comes out negative, then we don't have enough oxygen. So that's why we're calling this the oxygen balance. So in this formula for nitroglycerin, this is D. So we have 9 moles of oxygen. We have 3 moles of carbon, and so we're going to take away 6 moles of those oxygen atoms because of the carbon, the CO2. And then here we're going to take away 5/2 moles of those oxygens for the water. Okay. And then we're going to divide all that by 2 because we don't get moles of oxygen atoms, we get moles of oxygen gas. So if it produces excess oxygen, then that's going to come out as O2, and that's going to help push the wall down if we're blowing something up. So this turned out to be a positive number. So that's a positive number, which means we have a positive oxygen balance. And so again, we're dealing with the masses. So oxygen balance is in mass. So we want to convert those positive moles of O2 into mass of O2, and then we divide that by the molar mass of nitroglycerin. So we are positive by 0.035, or positive by 4%. So we have 4% excess oxygen in nitroglycerin. Now that's not everything for why it's so shock sensitive, but it also contributes to that. So we have nitroglycerin burns extremely fast. In fact, let's look at this. Let's do a propellant first, one that doesn't have enough oxygen, and then we'll see what we have when we have enough oxygen. So these are some videos. I have to work over screen here.
What's up, guys? Welcome back. Today is an exciting...
Okay, let me just, I'm going to pause the video and upload it in 3 parts. Let's see, can I pause it? Yeah, I'm going to show the shape charge simulation and then the actual video of it being used. I'm showing this because I'm afraid these are going to start showing up, and I would like for you guys to know what's going on if you see explosives, steel containers, and copper cones. For some reason, copper has the perfect properties for this particular function, and what we're doing is we're taking the explosive force, which typically pushes out in all directions, and we're concentrating it into a particular like pencil-like force. Okay. All right, so here let's do one for TNT, trinitrotoluene. So you got toluene, you nitrate it 3 times on the aromatic ring, and now these are nitrotoluene, not nitrates. Nitrates are NO3s. Nitro's NO2. We'll see some molecules in a second. But if we do this, here's the toluene molecule with 3 nitro groups on it, and we do the oxygen balance. Okay, we got 7. I think that's a typo. It's 17. Yeah, I think I hit. Anyway, I changed this this morning. It should be 7, not 17. 7 carbons. And we end up with a negative 5.25 moles of oxygen. What does that mean, negative 5.25? That means we don't have enough oxygen in trinitrotoluene to fully produce the amount of gas that we need. And so it still detonates, it's still an explosive molecule, but it could be better. You could get more energy out of a molecule that had a better oxygen balance. So we can take that, if we divide it by mass, we convert the moles of oxygen to mass of the toluene, we end up with the negative 74%. So it's pretty low in terms of its oxygen balance. So that's why we don't use TNT for our bombs anymore, are explosives because we have more we might use it in some formulations, but we have better explosives. And what makes a better explosive? One that produces more gas for less mass. And so here, to produce more gas, we have to have more mass of TNT. You can also look at the chemical evidence of burning, let's say in arson and so on. We have a whole lecture on arson, but I want to point here, chemically, if you've got any kind of solid fuel or whatever, like a candle, you use up energy to melt it, and then it becomes a liquid, and then you use up energy to vaporize it or decompose it. A candle decomposes, it doesn't boil, it doesn't vaporize, but it decomposes, and it's the gases that burn. So you need mixing, and so you need the oxygen to react with the gases that burn. Now, if you got a big molecule, like a big wax molecule, it's so big, it's not going to get volatilized. It's not going to be evaporating, but it'll decompose. So the heat from the flame will start exercising that molecule and activating its vibrations and work its way up the vibration chain and start ripping it apart. And so it'll decompose. And then whatever else is burning might decompose from the heat too. So this is a carpet. This is fuel poured on carpet and then set on fire. And so you can see the fuel is burning and then the heat is decomposing the carpet. But in the middle, you've got a protected area. Okay. If the fuel is there, that fuel has a certain boiling point, and that boiling point is likely below the decomposition point of the carpet. And so that as long as that carpet is wet with fuel, then it's not going to decompose. So that's why you don't see decomposed carpet out here. The fuel out here protected it, and then the fuel in the middle protected the middle. And so this is called a donut hole burn pattern, and that's a physical evidence, but the chemical evidence is sitting right there. And so if you ever saw a carpet pool fire, you would grab that middle piece immediately and put it in an arson can and then analyze the vapors. Now heat, this decomposition thing causes charring, and so we can see this. Arson produces burn patterns that are distinct. They typically give you a V pattern from the source if the source is low. So you see heat rises, that's the number one principle between investigating any kind of fire. And so you will see a char pattern follow that V, and that V will point right down to the source. Now let's talk a little bit more about this deflagration to detonation transition. Okay, and we use this to produce all different levels of explosives. So you can go from a small thing like a firecracker to a detonator to a booster charge to all the way up to thermonuclear detonation by coupling these shock waves. And so here's the detonators. You have a bunch of different types of detonators which would have all different kinds of chemical signatures. You would have maybe a pyrotechnic mix, something like we would call an electric fuse. This little orange piece, believe it or not, you can get at Hobby Lobby for rocketry. So you can go to Hobby Lobby and buy these little rocket starters. You put a voltage across a couple of AA batteries and it'll catch fire. It's a pyrotechnic mix. And you put that in the bottom of a rocket engine, countdown, 3, 2, 1, and then it catches fire and catches the propellant on fire, and then off your rocket goes. Okay, so they're called electric matches. But then you put that together with something, so you have a spark or heat, then you get combustion, it's confined, okay? And you start to build this wave front. And when that wave front starts to generate enough chemical reactions, enough bonds breaking and other bonds making, then you start getting light emitted. You get hot spots, and the infrared shock wave can go through the material. And once that transitions to faster than the speed of light, or faster than the speed of sound in the material, then you can get a detonation. These are much more. Oh, here's another electric match here. Right. In fact, that's exactly what it looks like at Hobby Lobby. Okay. And that's okay to sell those at Hobby Lobby because you don't have access to this other stuff. Okay. But if so you find somebody's garage and they got electric matches and they've got pentaerythritol tetranitrate and maybe some other kind of explosive, then you know you got a clandestine bomb lab. Be careful. You know, more high-tech ones would be these exploding bridge wires and slapper type detonators. And these would be military grade or some other kind of government sponsored activity. So let's look at the molecules. We've got a couple of minutes. So these are mercury fulminate and lead azide, lead stiffnate, nitroglycerin. These are all primaries. These would be in your detonators or in your primers for ammunition. So like all your rifle cartridges and anything that has a primer, we put one of these primary explosives in that primer can, and when the firing pin strikes it, it causes the reaction. They're shock sensitive. Then you have propellants like nitrocellulose, and then this is a primary too, this pentaerythritol tetranitrate. So PETN. Erythritol is kind of a really cool molecule. It's a carbon in the middle and it's got 4 carbons around it, and then those 4 alcohols. So it's like a 4 alcohol molecule. The carbons form a tetrahedron and then you have OH groups on them. And if you nitrate those, then you have pentaerythritol tetranitrate, 4 nitrates. These are the main charges, the high explosives, and there's different chemical classes I want you to know. The simplest to remember is the nitroaromatic. You see it's an NO2 on an aromatic ring. So that's what trinitrotoluene is. Picric acid is the same thing, but it's with a phenol. Very dangerous molecule. It's used in some biochemical assays, and so biochemistry labs sometimes have picric acid in them, and they're very dangerous. They have to stay wet, otherwise they become shock sensitive. And if you ever see a dry bottle of picric acid, do not touch it. Call the hazmat team. We had one at West Texas A&M. They came and very carefully put it in a rubber bucket, took it out to the farm and shot it with a high-powered rifle. And it detonated and left a big old, like a 1-foot crater in the dirt. But that would have been a bad thing to happen in the lab. This is the least sensitive explosive that I know of, triamino trinitrobenzene. So again, these are nitros. There's 3 of those. There's 3 amines. But let's look at these nitramines. So look at this. This is a nitro group hooked to a nitrogen. So nitramine. So you see the amine piece is right here. And then the nitra part is the nitro. So nitramines are very common. HMX and RDX are nitramines. And then this tetryl is both. It's a nitramine right here. So that's a nitramine, and then it's also a nitroaromatic. So it's in both categories. And then we're kind of out of time. But anyway, we can just build that explosive train up from the detonator to a booster to a main charge to subcritical masses that would do fission, like uranium-235. And then if you put tritium in between those, you can get fusion. And that's be called a boosted fission weapon. So it's just matching, sort of impedance matching the output of one explosive to the input of the other. And you can go as high as you want, all the way up to fusion. Okay, so I guess the last comment would be mixing in, they call this blast enhanced explosive, Cybex, mixing in metal powder. So you can have the explosion disperse aluminum powder, zinc powder, anything that reacts with oxygen well. And that will produce an enormous fireball that has an enormous amount of energy released. And so the aluminum oxide reaction gives off way more energy than carbon dioxide or water. And so it just produces a huge burst of heat. And that heat then pushes air, hot air expands. So we have the initial explosion, and then we have this overpressure wave, and it's this push for a long time that knocks things down. And so these are the thermobaric weapons that just destroy structures. They used to also use them to knock down trees. They can drop one of these in and knock down the trees, and then helicopters can come in and land. So they would use them in Vietnam to make a landing zone. They drop one bomb down, knock out the trees, and then the helicopters come right into the middle of the jungle. And so this has been around for quite a while. What would be the chemical clue to this? Would be aluminum powder mixed with, with explosives and so on. So that's a telltale sign that someone's making a thermobaric explosive. Very dangerous.